So this is coordinated with the Western Hemisphere Symplectic seminar. And the first talk is going to be given this morning by Rita Pires. She's gonna speak from Edinburgh. And she's gonna speak about infinite staircases and reflexive polygons.
All right. Yes, thank you. So let's see. First of all, thanks to the westernmost and easternmost people. I see that I recognize some names. So I think there are some people for whom it is 6:15 a.m. Oh, thanks for waking up early. All right. So this is part of Ellipsoid Day. Let me get. Oh, I see. Sorry, just moving things out of the way here. Okay, so I realized that I forgot to put my affiliation. There we go, but it's University of Edinburgh, as Octavian said. And then these two talks, oops, let's see, are Western Hemisphere Virtual Symplectic Seminar. All right, and I know that at least Renato is here, and Dan is here, and Tara is here, and Alessia is here. And hopefully Roger is asleep. Right, how do I, here we go. Okay, so the original Ellipsoid Day is actually April 27, 2020, when the 3 papers showed up on the archive. So it was this one, which is, so here's our picture. I put this picture here to plug the IAS Summer Collaborators Program. So everyone, if you have collaborators and after the pandemic you want to spend some time with them in Princeton, this is a good thing to do. And then the second paper was this paper by Roger and Renato. Oh, it says 28th of April. Well, they all showed up on the same day. And then this one, what happened? Where is it? Oh, well, we're missing Dan's face. So here was Dan's paper, and here was a picture of Dan with a beautiful background. I don't know what happened. There, sorry, I apologize. Oh, it's deleting my things. Sorry, let's see, let's hope this, this works okay. All right, so the beginning of this story is this paper of Dusa and Felix. Hi Dusa, hi Felix. From 2010 about the embedding capacity of 4-dimensional symplectic ellipsoids. So the I copied this little bit of the abstract that says what it's about. So it calculates the function whose value at A, and I have here the formula, whose value at A is the infimum of the size of a ball that contains a symplectic image of the ellipsoid E1A. Right, so I put here CB4 because we're going to talk about this for other targets other than the ball. Oh, sorry, still getting used to the technology. Okay. So by contains, so just a little bit about the notation and the language. By contains a symplectic image of the ellipsoid, we mean there exists a symplectic embedding, which is a map between 2 symplectic manifolds where the symplectic form pulls back. You can have the dimension of M2 be bigger than or equal to the dimension of M1, but the most interesting case is when they're equal. So that's what we're going to be, well, that is the case in this paper, and that is what we're going to be talking about here. Then this is an ellipsoid. So, you know, here, I'll draw an ellipsoid. So A1 would be the area of this great, well, quote unquote, great axes, and then A2 would be sort of the area of this, where that should be the 3rd and 4th dimension. great axes. And then the ball is just the ellipsoid where both sizes are the same. And we can actually replace infimum by minimum in many cases, including this one, but infimum is more general, so I'll leave it like that. Okay, so they say the abstract says the structure of the graph of C of A is surprisingly rich, which is an understated way, I think, of saying that it's amazing. So here is the graph of the function. So we have it's this little these stair steps. So I should say, so I have here the volume constraint. Oops, volume constraint. So that is because if you have a symplectic embedding of an ellipsoid into a ball, or of something into something, then the volume of this one has to be smaller than or equal to the volume of that. And by just computing what those things are, you conclude that this lambda always has to be bigger than or equal than the square root of a. So the value of the function is bigger than or equal than the square root of a. So I have here in red the square root of a, and then the graph of the function. And so I'll put some numbers here. Yes. So the origin is at a weird place, just so that more graph fits. And so this has this point has height 1, this point has height 2, this point has height 2.5, which I'll write as 5/2, and then the next little step has height 13/5, and then that one has height 34/13. And you might recognize these numbers. They are the 1, 2, 5, 13, 34 are odd index Fibonacci numbers. So this was baptized, the Fibonacci staircase. And each of these segments is either horizontal or linear through the origin, which again, the origin is not here at the origin of the axes. Then from, I don't even know exactly where it is, let's say it's here, from 17/6 squared onwards, the function is just equal to square root of a. And here in this middle, there is, it's often equal to the volume constraint, and then there are some little intervals where it's linear. So we'll put mixed behavior here. We'll just put mixed. And the other thing I should say is this point right here, where the little steps accumulate, that has coordinates tau to the 4th, tau squared, where tau is the golden ratio. And of course, if you have Fibonacci numbers, you shouldn't be too surprised that you get something related to the golden ratio. But still, it's still surprisingly rich. Sorry. I was just saying that you can only be surprised about one thing: Fibonacci numbers or golden ratio. You can't be surprised about both. The other thing that I want to note here, just for future reference, is that these points where I have my function touching the volume curve, so you'll see what this means is that the ellipsoid actually completely fills the ball, or fills 100% of the volume of the ball. So these correspond to these actually correspond to full embeddings. Well, I guess because I said that you could replace inf by min. Okay, so you actually have a full embedding of the ball. So in the next slide, I want to talk about two questions. One is why did they think of looking at this function? And then the other one's about the infinite staircase behavior. So a little bit of related ideas. to this function. We had, well, I guess the most famous or seminal, the most seminal one is Gromov non-squeezing. A ball embeds symplectically into a cylinder if and only if it embeds by inclusion. So I won't put formulas because I think that everyone here knows the statement. There's also the idea related, the idea of Gromov width of a symplectic manifold. So what is the size of the biggest ball that embeds symplectically into a symplectic manifold? Then this idea of packing stability, that there's no obstruction beyond volume to embedding a collection of small enough balls into a certain class of symplectic manifolds M. And packing stability is also what is happening there at the end. Here in this part of the function, that's a version of packing stability, because it turns out that embedding an ellipsoid is equivalent to embedding a lot of disjoint balls. And then perhaps more closely related to this question, this Hofer conjecture on ellipsoids, solved by Dusa. I never know if I should say the last names or the first name. It sounds weird to say Helmut's conjecture on ellipsoids, but then it says, it sounds strange to say solved by Macduff. So anyhow, let me continue. Which is about when an ellipsoid embeds into another ellipsoid. And it turns out to be a very simple to describe combinatorial relation between A, B, C, D. I guess I shouldn't say simple to describe because I didn't write it because I found it hard to describe in a line, which is where it fit in the slide. But it has to do with integer linear combinations of the numbers A and B compare with integer linear combinations of the numbers C and D, and order them, and then if one collection is always smaller or equal to the other, then it embeds. And it turns out that those numbers are ECH capacities of the ellipsoid. So we'll go back to that, to ECH capacities, that is. So the second question is about this infinite staircase behavior that is observed in this ellipsoid embedding function for the ball, which is this a characteristic of the function? And does it happen if you replace the ball by anything else, or is it a characteristic of the ball? So here's how one can extend the definition for other targets. So it's the size of the smallest scaling of X into which an image of the ellipsoid that contains an image of the ellipsoid. And then we can ask, what does this function look like for other targets? So in general, this function is piecewise linear when not equal to the volume constraint. And we say that it has an infinite staircase if it has infinitely many non-smooth points. So then, now that we have this language, we can ask, does it always have an infinite staircase? If yes, why? What is it about this function that always makes it have an infinite staircase, which is a strange behavior? And if not, then when does it and when does it not? And why does it and why does it not sometimes? Let me also, just to complete here, mention some other work on infinite staircases since this paper of Dusa and Felix. There have been infinite staircases found and proved for the polydisk by Frankel Muller. I should put here now that, okay, there we go. For these ellipsoids, I guess the first one is actually the ball, and E12 is actually, in some sense, the same problem as D1 cross D1, and E23, the other ellipsoid. So this is work of Christopher Garden Kleinman. Then Mike Usher thought about infinite staircases and proved that they exist for certain polydisks D1 cross DB. He focused on the case where B is irrational, B not in Q. And then all of us, so Maria, Tara, Emily, Dusa, Grace, myself, and Morgan, this is work in progress. Let's see, work in progress. Is this, I don't know if this is the thing that mathematicians write or only knitters. I know that knitters use work in progress, like that, WIP. And then also Roger and Renato worked on an aspect of the infinite staircases and these full embeddings that I was mentioning for several different targets. And there's a talk later about that. Okay, so this question of when does the function have an infinite staircase and when does it not? So one of the theorems that I want to tell you about today is this staircase obstruction theorem, baptized yesterday with this name. Which says if X is a closed toric symplectic manifold, or more generally a convex toric domain with finite blow-up vector, then if you have an infinite staircase, we know exactly what this accumulation point, which for the ball was tau to the fourth, at tau to the fourth, we know exactly where it has to be. So it accumulates at A naught, which is a real solution of this quadratic equation. And furthermore, so that's the one coordinate, and the vertical coordinate has to be square root of A naught over ball, which is this volume curve. It's what replaces this volume constraint that I had in red for the ball. So this has a lot of, I'm going to use this theorem as an excuse to introduce a bunch of language and ideas. So so question one is, what is a convex toric domain with finite blow-up vector, and in what way does it generalize a closed toric symplectic manifold? I say here that the infinite staircase accumulates at A naught, but the definition of infinite staircase is just that it has infinitely many non-smooth points. So it could never accumulate, go off to infinity. So why doesn't it? The other one is a bit of a silly question, which is a quadratic equation usually has two solutions. What happens at the other one? Then what are these numbers? What does pair and vol means? And finally, I'll just remind you, what is the volume curve? And then another question is, so this is an obstruction theorem, so how good is this as an obstruction? So it just says if it has an infinite staircase, then it accumulates at A naught, but it doesn't have the other direction. So let me talk about that first. So I have here in very small, it's the same theorem, just to remind you. So here's what happens usually. So for example, at the ball, you have here, this is, oops, let's see, let's change to black. So here's my A naught, and here's my A naught. So here's the typical behavior. If there's an infinite staircase, well, this is what the theorem says, then there's A naught, and the function is equal to the red curve, the volume curve at A naught. And when there is no infinite staircase, this is typically what happens. You have A naught, of course you can compute what it is. Well, it might not be a real number, in which case you don't have an infinite staircase. But if it is a real number, then here you have, so C sub x of A naught is different, or is, how do I erase? Strictly bigger than square root A naught over vol. So I said this is typically what happens. Oh, don't worry about this notation yet. We'll get there in a bit. This is just something, I'll just say that this target, this X, is in some sense very similar to the ball. And you can see that there are some similarities in the graph, which is an interesting thing. But what was I saying? Ah, yes. So this is typically what happens if you have an infinite staircase. That's where A naught is, and that's what the theorem says. And if it doesn't have an infinite staircase, typically what happens is that the function is obstructed at A naught. In fact, we only know of 2 cases where here's A naught, and where the function is not obstructed at that point, but there is no infinite staircases. So this is the ellipsoid E43, and the other case that we know is let's see, CP2 blown up 4 times. Let me see. Ah, did I not write it down? I think, let's see, let me think. I think it's 4 CP2 bars. I think that either Dan or Alessia or Dan will be able to tell us in the chat if I said something wrong. It's either 4 or 5. I think it's 4. Okay. So the thing, so this one, E43, and these are the only 2 cases that we know where this happens. But it is also true that for both of these, A naught is a rational number. And so it might be that it is possible to prove that if the solution of this quadratic equation is irrational, then we have an if and only if. And so it would be sort of a complete, I don't know, total perfect obstruction. I don't know what the correct mathematical term would be. Okay. So let me go back to introducing to these questions. So the first question was, what are convex toric domains and how do they generalize closed toric symplectic manifolds? Okay, so sorry, just looking at my notes to see if I have everything. Okay, so if you think of this map, which is actually the moment map, so here, I'm pointing at it, but of course you can't see unless I draw something. This map is actually the moment map for the action of T2 on C2 by rotation. And we define a convex toric domain to be the inverse image under this mapping of some convex region in R2. So if you think about what this first one is, so that is the points in C2 such that Z1 squared, such that this plus that, we'll put some ones here, such that this plus that is smaller than or equal to 1. So that would be the ball B4, 1. Oops. Oh. I think that it's good that we're having all these online seminars now, because it's helping us practice for teaching like this in the fall. And then if this is A and B, then you can conclude that this would be the ellipsoid. If this was 1 and 1, this would be the polydisk. I'll call this P11. And then if this is A, B, this would be this polydisk with different size disks. And then this is, well, this other one is just, I don't have like a short way to write it. Let's see, okay. So it turns out that a convex toric domain can be described in terms of a blow-up vector. So let me explain briefly what that is. So if you have a shape like one of these that I drew here, you can think of carving it out of a triangle in the following way. So I'll do it with, maybe I'll do it with this one first. Let me get a red pen. There we go. So here, if I start with this is a triangle of size A plus B. It's a very thick A plus B. And then if I remove a triangle of size, so that would be a triangle of size A, and I remove a triangle of size B, then I'm left with this rectangle. So I would say that the blow-up vector here is A plus B, A comma B. Okay, so that's change pens. It's pretty ridiculous to write so thick. So here I'd have some, oops, well, that is not very pretty. So here I would have, say this is size, I don't know, 4. And then this one is size 2. And then this one says size 1. So that would be the blow-up vector. Now I should say that a blow-up vector, this function that, given a shape gives you a blow-up vector, that's not unique. So it's not well defined, and vice versa also not, because of course I could start with a bigger triangle and then just carve out more things. But that's okay. We don't mind that. And then the other thing that I should say is you'll notice that I have here, I don't have, it just doesn't necessarily end. So for example, in the ellipse, it can be infinite. So for example, infinitely long. For example, in the case of the ellipsoid, if B over A is an irrational number, then you'll have an infinitely long blow-up vector. All right, and then so this is an explanation of what convex toric domains are. And now, how do they generalize closed toric symplectic manifolds? Well, one way of thinking about that is there's this result. This is a slightly weaker version of what Karchan, Kessler, and Punsello prove. But that says that any closed toric symplectic for manifold is symplectimorphic to CP2 or to CP1 cross CP1 blown up a finite number of times. I should say, I guess, to there. That's how that should be parsed. And so you can see that that's very similar to this idea of the blow-up vector, because you're sort of starting with a CP2 whose moment image is a triangle, and then you're blowing up a certain number of times, and that corresponds to chopping off corners, little triangles at the corners. And the other thing that is useful to see how this helps generalize in this context of our function is that symplectomorphic manifolds have the same ellipsoid embedding function. And so right, and so the fact that any closed symplectic for a manifold is symplectomorphic to one of these means we only need to worry about these guys. All right, so and the other ingredient that we need to explain why convex toric domains generalize closed toric symplectic manifolds is this very useful result, or looks unassuming, I think, but is very useful. We end up using it many times, is that if you have a convex toric domain and a closed toric symplectic manifold that have the same moment image, then an ellipsoid embeds into one if and only if it embeds into the other. And so in particular, they have the same ellipsoid embedding function. So we keep reusing this at several stages of the proof. All right, so hopefully I convinced you why, even though it's sort of more natural maybe to think about closed toric symplectic manifolds, it is good to think about convex toric domains. All right. And then the second question, so here's just the theorem again, the staircase obstruction theorem, and the leftover questions. So why does it have to accumulate at a finite point rather than going off to infinity? So that's, I already hinted both of these things, I already mentioned them. For a convex toric domain, embedding an ellipsoid into it is the same problem as embedding a bunch of disjoint balls. And the balls, of course, the AIs are determined by A, but I won't go into detail here. And then this packing stability property about how there are no obstructions beyond volume to embedding a collection of sufficiently small balls. And so what this is saying is that for large enough, at some point, there's some A for which after that A, C sub x of A is just equal to the volume constraint. There's no other obstruction. Okay, so just looking at the notes again. All right. Then the third question was about how the quadratic equation usually has two solutions, and I'm only talking about one. So E1A is the same problem as E1 over A, because it's a rescaling, essentially a rescaling. And so there's this involution there's this symmetry about A equals 1. And so we actually usually only think about this function for A bigger than or equal to 1. And so whatever happens on one side, if you have a staircase for A bigger than or equal to 1, then you have a tiny little staircase on the other side. Oh, there we go. Put an equal here. Oh, I think it's because I was writing this just with the text function rather than the LaTeX, and it doesn't have greater or equal. So I was lazy and just put greater. Okay, then the fourth question is about these this pair and vol. So if your convex toric domain has moment image omega and this bulk vector, then the pair is just the affine perimeter of omega, which you can compute as 3b minus sum of the bi's, and the volume is the volume is actually the symplectic volume of the convex toric domain. It's 2 times the area, and it has this formula. And one thing that I wanted to note is that pair squared over vol is invariant under scaling. So it's an invariant of the shape. It's actually an invariant of the blow-up vector even more than the shape, because each blow-up vector can be realized as several different shapes. Then finally, what is this volume curve? So that's just the correct generalization of this square root, this red square root A that I had in the graph for the ball. So if an ellipsoid embeds into a certain scaling of x, then the volume of the ellipsoid has to be smaller than or equal to the volume of that scaling, which translates to A smaller than or equal to t squared times vol, which translates to that. So, okay. So that's this staircase obstruction. So this idea of trying to answer, why does it, when does this function have an infinite staircase and when does it not? How can we tell? So this is really a very important step, well, I think, in being able to answer that question. What I want to tell you about next is one instance in which we used this theorem. So it's a beautiful part of the story about infinite staircases for different targets, which is to look at when the blow-up sizes are all rational. So, well, more than the blow-up sizes, also the first one that you start with. So we look at x equals, it has this blow-up vector where all of them are integers, because with scaling, of course, if it's rational, you can scale it up so that everything is an integer. So here's a very, I think, very pretty result, which is if there is an infinite staircase in the ellipsoid embedding function, that forget the if, that every one of these, of the convex toric domains with these regions have infinite staircases. So let me just, yes. So here are some familiar ones. So this one's the ball. Let's see, this one's the polydisc. Here is E23. I think I had also written E12 as one of the ellipsoids. So this one's 2 times E. It's a scaling of E12. I forget, I think that's all the ones that I had written there. And you can see here that there are this thing that I was saying where you have 2 different shapes for the same blow-up vector. So for example, 4, 2, 2, it's either a square or this E12, or 2 times E12. But if they have the same blow-up vector, then they have the same function, embedding function. So about this theorem, I want to deal with 2 questions. One is, what do these staircases look like? How are they similar and how are they different? And also, how does one show that there exists an infinite staircase for a given x? Or how do we show that there exist infinite staircases for these convex toric domains? But before I do that, I just want to say that you may recognize this family of shapes. And if you do, then you may notice, you may complain that there are 4 shapes missing. So here they are, they're the ones that are missing. So this is the 1, 2, 3, 4, 5, 6, 12, 16. These are the 16 reflexive polygons. So lattice polygons with exactly 1 interior lattice point, but these 4 ones, they don't have an infinite staircase. We checked. Okay, and I do owe you the discussion of those 2 questions, but I also, while I have this theorem here, wanted to say that we conjecture that these are these 12 examples are the only rational ones with infinite staircases up to scaling. Another way of saying it is that if C sub x of A has an infinite staircase, and we're in the rational case, then the moment polygon of X is a scaling of a reflexive polygon. And so in addition to discussing those 2 questions that I was mentioning, hopefully I'll also be able to tell you a bit about why we think the conjecture is true. So what do these staircases look like? So here's the ball that I already had drawn, and here's the polydisc and E23. And you'll see that they're all, they have, oops, no, okay. Sorry, I thought there was a chat, but it's on the wrong computer. Okay, right, so they all look fairly similar. There's maybe, to me, what seems most, the difference that to me is most striking is that in these 4, you have these full embeddings happening. So your interior corners of the staircase are hitting the volume curve, and then these 2, they are not. And I'll mention here just that the same way that in the ball, the heights have to do with ratios of Fibonacci numbers, and the Fibonacci numbers, or rather odd index Fibonacci numbers, are a sequence that satisfies a recursive relation. The recursive relations that rule these 4 in the bigger circle, they have, in some sense, a recursion of order 2. So I'll just put here j equals 2. And for these, they have a recursion of order 3. So there's something in the numbers that is encoding this difference. Okay, what I mean by order 2 is if you have Fibonacci numbers, well, if you have odd index Fibonacci numbers, how should I say this? The 4th term is determined by the 1. Sorry, let's see. Let's not say anything about this. Okay. Sorry about that. Okay, so how does one prove that an infinite staircase exists? Okay, so we first, let's talk about some basic properties of this function. So it's continuous. It is non-decreasing. It has this scaling property. I'll point out where it's important, that scaling property, but don't worry trying to decode it if it's not obvious right away. Equal to the volume curve for A much bigger than 1, so that's this packing stability, and piecewise linear when not equal to the volume constraint, which I had already mentioned. So the way that we proved it, and the way that one can prove, is by trying to establish the existence of these points that are in the big circles. In particular, what you need to do is, let's see, I need a black pen. Okay. You need to show that the function cannot be anywhere under here. This is very similar to a picture that I saw Felix draw in a talk. I really like this picture that he drew. So for the green dots, for the outer corners, you need to find an obstruction, which will guarantee that the function is not down here, right? It has to be above that green dot. And for the inner corners, you need to show that the function cannot be above that value. And if you do that, then because the function is non-decreasing, you get this whole horizontal line between a green and a blue. And because of the scaling property, because a blue dot and a green dot are in a line through the origin, this scaling property actually tells you that this is what the graph has to be. It has to be aligned through there. So those are the two ingredients. And the way that we find these corners is, for the outer corners, we find an obstruction, we use ECH capacities, and for the blue dots, for the inner corners, we find an embedding. In our case, we use almost toric vibrations. If you want to show that there's an infinite staircase, I mean, I think there are other ways that you can show that these corners exist. You can also, for example, if you don't want to show certain corners like the blue ones, you could show that the function is equal to this little elbow around each green corner or something like that. But it's very satisfying to erase things here. Okay. All right, so let me talk a little bit about each of these. So for the green corners, yes. Okay, so for the green corners, I said we use ECH capacities. So ECH capacities are introduced by, again, first name or last name, by Hutchins. And then Dan proved that in the problem of embedding a concave toric domain into a convex toric domain, for example, whoops, still the eraser, for example, an ellipsoid into a scaling of a convex toric domain, the ECH capacitors are sharp, which means that this embeds into that if and only if this sequence of ECH capacities is smaller than that sequence, and then you just pull the lambda out and you get that, which means that if C sub x of A, which is the infimum lambda such that this happens, is you can also write it as a supremum of this ratio of ECH capacities. So ECH capacities of an ellipsoid are in some sense easy to compute. They are, it's this thing about the integer linear combinations of 1 and A in this case. ECH capacities of some convex toric domain are harder to compute. And so there are several ways that you can go about this. The way that we used has to do with counting lattice points, the in some sense, the length of a lattice path encloses a certain number of lattice points, and for each x, oops, we had to find a different shape lattice path. So that's how we found one of these. So what we did is just find a k, find a certain k for which you get that height value, and then because this is the soup, you know that it's that or higher. So then that gives you this thing. Okay. Then for the inner corners, we use this almost toric vibrations. It seemed at the time. Okay, 15 minutes. So the fact that I'll tell you in a moment what 8EFs are, or maybe I should say, let's see, what should I say first? Okay, so 8EFs are initially due to Margaret Symington, and what the basic idea is that you no, let's say this in the other order. I apologize. Okay, so the fact that we could use this idea of almost toric vibrations to do this, so the fact that you could use almost toric vibrations to recover these numbers that represented the inner corners in the case of the ball and also of the polydisc. This was an idea that Roger Casals suggested to us a few years ago. Actually, I have to say that the first time that I heard this idea, I was not ready to digest it. It was Ivan Smith had written this paper with Johnny Evans about Markov numbers in Lagrangian cell complexes in CP2, and he mentioned that these Markov numbers were very similar to these numbers that were showing up in the Macduff-Schlenk Fibonacci staircase. And I was not ready to hear that. And only years later, when Roger mentioned this idea of his, and was I able to process, and then it became this beautiful part of the argument, which is a much more elegant way to get the interior corners than what we had before, which is a little bit messy. Well, it wasn't messy. It was just not as elegant. Didn't have such nice drawings. Okay, so almost toric vibrations are an idea of Margaret Symington, and in our proof we also actually use some constructions of Renato, who's in the audience, and who is a co-author in this paper that Roger is going to be talking about full embeddings. So the basic idea is that you manipulate diagrams representing a closed toric symplectic manifold. It's important that you start with closed toric symplectic manifolds. So you have a diagram representing this closed toric symplectic manifold. You can start with its moment image is maybe the easiest. And then you do these manipulations which have to do with, so I'll just draw here, for example, if you start with the square, you have this ray going in, it's a direction that makes this be a Delzant corner and this also be a Delzant corner, if you know what that means. And then you sort of extend it here. In this case, with the square, we're very lucky, and it hits that other corner. And then in the new diagram, you leave this part unchanged, and then this, whoops. Oh, what are you doing? No, I don't want, whatever you're doing, I don't want to do. Okay. And then you take this one and you do this affine transformation and so that this side is going to go flat here. And then it sort of, and this side stays where it is. So there we go. And then it becomes, in this case, it becomes a nice triangle. And then you do it and then you do it again, but now you do it at this corner. You have like a little ray in here, and you continue. So you manipulate these diagrams, and this manipulation, it doesn't change the underlying symplectic manifold, but does change the Hamiltonians that map onto that diagram. That in the beginning, in my examples, were the moment map, the components of the moment map. And what we do is we prove that if a triangle fits in one of these diagrams, sort of anchored at the bottom left, at the origin, then in fact, the corresponding ellipsoid embeds into the manifold that you started with. So the embedding is not at all obvious from the diagram because, of course, the diagram has been affected by this sequence of modifications of Hamiltonians, but still you get your embedding. So let's see. So here's an example. Here's, we start with E11, so the ball. And then in the first mutation, you get this shape, this E122, and E122 is 1/2 of E14. And I write it this way so that you can compare with this thing here. So note that E1a embeds into lambda x if and only if 1/λ, E1a embeds into x. And so what I'm saying here is that 1/2, sorry, lambda. So for lambda equals 2, you have E14 embedding, right? And so that's here's the 2, and then, oh, sorry, nope, wrong place. This is, of course, the sound that erasers make. So here's the 4 from E14, and here's the 2 from the 1/2. Okay. And then here's 2/5 and 25/4, which is 5/2 squared. Sorry, 2/5. So the height, remember, that was the 1, 2, 5/2, 13/5, and so on. And then these numbers give you the a coordinate of the function of the blue corners. And so if you start with, for example, with a polydisk, then you get, if you start with a square, then in one step you get a triangle, and then forever you have triangles. If you eventually get a triangle, you get triangles forever. It might happen that you don't get a triangle. So for example, here's E23, sorry, here's this, it's like a Hirzebruch surface. And you can see that E23 fits in there. And then you do a modification, you still have a quadrilateral, and now your ellipsoid is, your triangle is taking up more space of the quadrilateral, and more and more and more, but it will never give you a full filling. And here's the magic of virtual things. Here's what's happening with that infinite staircase. You don't hit the volume curve, but you get closer and closer to a full filling. So, and that's the J, what I said, the J equals 2 versus the J equals 3 case. Here, you only have 2 extra corners that you're mutating on, and here you have 3 extra corners that you're mutating on. So that's where those two things tie together. All right, and the other thing that I wanted to say was about this must start with closed toric symplectic manifolds, but then I keep talking about convex toric domains. Well, this is one of the places where that theorem about embedding an ellipsoid into a closed thing versus a convex toric domain comes in handy. So we use it there. All right, so just this is, oops, okay, very quick. Cute short proof of where a knot is, so the fact that it's a solution of this quadratic equation. Now it uses several assumptions. It uses that the interior corners of the infinite staircase are given by almost toric fibrations, which I don't know if that's true for every staircase. I don't know, for example, if Usher's staircases are given by ATFs, or the ones that this long list of people Dusa and Grace and Tara and Morgan and Emily and Maria. I don't know if those are given by ATFs. The other assumption is that the accumulation point A naught is irrational, which is a pretty big assumption. And if that were true, then the theorem would give you a complete obstruction to when there are and there aren't infinite staircases. And the fact that E1 A naught gives a full filling, so that's the thing about C of A naught is equal. So knowing this part, that's that half of the theorem. But if you assume these two things, then if you start with some shape X and then do these manipulations, and in the limit, you get your ellipsoid that is at A naught, at the accumulation point. And it turns out that this iterative process doesn't change the area or the affine perimeter of the shapes. And so you can equal the vol and the pair, the area, the vol and the pair of this one and the vol and the pair of that one. And then when you sort out what these things are, well, you get this one, which was an assumption. But then you also get our quadratic equation. So that's just, I thought that was pleasing. So I wanted to show you. All right, so I answered those two questions, and now I have 6 minutes left. And I wanted to tell you, the other thing that I wanted to say was this, why do we conjecture this conjecture? So before I proceed, I have to say that it's very important for this conjecture that we have this rationality assumption. Okay? In fact, there are infinitely many infinite staircases for irrational convex toric domains. So one result is in this paper of Usher about infinite staircases for embedding ellipsoids into polydiscs, 1 beta, where beta is irrational. One thing I have to say, this paper has one of the coolest references that I know, which is this Brahmagupta's I can't pronounce that, which is from this 628. That's the year that it was written. So it's in Sanskrit too. And then the other case of looking for infinite staircases in irrational convex toric domains is so this is us at ICERM last summer, and we are looking for infinite staircases for Hirzebruch surfaces. So when you have the blow-up vector 1, b. So let me just take a minute here to talk a little bit about that. So here's so you can make, if you're looking at Hirzebruch surfaces of the form 1, b, then you have this parameter b that can vary from 0 to 1. Here is, so for b equals 0, you have the ball, or maybe I should say CP2. And for b equals to 1/3, you have this 3/1, or rather in this notation, 1 1/3. And those are infinite staircases, ascending because they're coming from the left. So you're ascending into the accumulation point. So we've shown that there are these blocked intervals. So values of the parameter. So here, values of the parameter where we know that there are no infinite staircases. Then we found some very intriguing descending infinite staircases. So that means that they're coming from the right. They're descending towards the accumulation point. And then we actually conjecture that there are a lot more infinite staircases and more blocked intervals, and there's a relationship between blocked intervals and infinite staircases. And so in particular, we conjecture that at the endpoints of blocked intervals are more infinite staircases coming from the left or from the right, one in one side and the other of the blocked intervals. So stay tuned. Okay, but so let me go back to telling you about the conjecture. So the idea behind the conjecture, this I know that looks awful. It has so many formulas, but let me guide you through it because there's a prize at the end. Okay, so you start with an x with integral blow-up vector. If it has an infinite staircase, then you know that that ellipsoid embeds into that scaling. And then this is the ECH capacities that I already had a similar thing to this. Here I wrote U naught and V naught to mean these things here on the right because that's too large to write. And then one way that you can write this inequality is you can define this function cap that counts how many ECH capacities are smaller than some number t. And so what this translates to, what this inequality of ECH capacity sequences translates to is this inequality between cap functions. And then if you think about what the cap function is for an ellipsoid, because the ECH capacities of an ellipsoid have to do with integer linear combinations of, in this case, U naught and V naught, it turns out that if you think about it for a little bit, it counts the number of lattice points inside a scaling of a triangle. 1 over U naught, 1 over V naught, and then you scale this by, I should put the T on the left, but it doesn't fit, so I'm going to put it on the right. So it counts the number of interior lattice points here, and that's just what the Ehrhart function is. And then it turns out that the Ehrhart function is, it looks sort of like a polynomial, except that this last term, this d of t, can be not constant. And on this side, the capacity function. So this was a conjecture for a while, but a couple of days ago, there was a paper on the archive that, so that's for this, that says for the x's that we care about, and possibly more, this is a quasi-polynomial. Or eventually a quasi-polynomial. So for t large enough, it is. And this term here, the thing that should be a constant in order for this to be a polynomial, it's not. So here you have a number that just depends on the congruence class of t mod vol. And so then this inequality boils down to this term d of t being bigger than or equal than this gamma r of t, which is just a finite collection of values. So what I want to say is that if you follow this implication and now you think of the converse, it means that if you want to show that something does not have an infinite staircase, then you just need to find one t for which d of t is smaller than this gamma r of t. And gamma r of t, like I was saying, is just a finite collection of numbers. So if you show that d of t is gets small enough or large enough but negative, then that would tell you that there is no infinite staircase. So Hardy and Littlewood studied actually this function, this d of t, but for them t is, and they consider t to be a real number. So I put here x, and they showed that this is optimally plus or minus O log x. They didn't use that notation. What it means is that, let me make this bigger, it's O of log x plus it actually goes above and below plus and minus log x, which is what we need. The only problem, of course, is that they're doing this for x in R and we want it for t in n. So that result of theirs does not take us there. But experimentally, we observed that this, if you just restrict for t into a natural number, then this d of t is either periodic or optimally plus or minus O log t. And it's periodic exactly when omega is a scaling of the reflexive polygon and optimally plus or minus O log t otherwise. Okay, so here's some evidence. If t divides pair, remember we only want sorry, if pair divides t, remember we only want one t, where that inequality doesn't hold, so that you can show there's no infinite staircase, then you can check that d of t is the sum of these two functions for a naught and 1 over a naught. It's a function, this is fractional part. Fractional part. So this is a function that has been studied by, has been extensively studied even by Sierpinski, which I was surprised about. And here's, we computed it, we have graphs for many, many examples. And if it's an integer, if a naught plus 1 over a naught is an integer, it turns out that the function is just constant equal to 0. And then if it's not, then it seems to be, we think, plus or minus O log t. And if it's if this special value, which turns out to be pair squared over vol, if it's a rational but not an integer, which again, remember, pair squared over vol depends on the shape, not on the scaling. So scaling will not make it become an integer. This is takes a finite number, so a discrete set of values, and here the lattice polygon is not the scaling of a reflexive polygon, and here this is one of Usher's infinite staircases, this one on the right, and here it's not even rational, and you can see it's a big mess. Okay, Octave, how am I doing for time?
You're doing very well.
I have one more slide.
You can take a few more minutes if you want. It's fine.
Thank you. Okay, so the last thing that I should say is this idea of why is it that periodic has to do with scaling of reflexive polygon. So this is just a repetition. Oh, I think maybe I didn't say it in the other slide. We're always assuming that a naught is irrational. The case where it's rational has to be dealt with in a separate way, because obviously it does not hinge on this special size ellipsoid E1 a naught, and including into this particular scaling of the target. So this part is just a repetition of the previous slide, a summary. And Christopher Gardner, Lee, and Stanley studied the Hare-Hart function, which was this one, Hare-Hart function of triangles, where U and V are, their ratio is an irrational number. So if they're, by the way, if their ratio is an integer, then D of t is a constant. If their ratio is a rational number, then D of t is periodic. And if it's not irrational, then in general, it's a big mess, D of t. So what they studied is for exactly for which U and V's is the function a quasi-polynomial. So is D of t actually not a mess, but rather periodic. So this is some period collapse behavior going on. And it's exactly when 1 over U plus 1 over V and this other one are integers. And in our case, with what U naught and V naught were for us, so these guys, which was square root vol over a naught and square root a naught over vol. This is pair over vol and pair squared over vol. Here's pair squared over vol again, keeps showing up. So let me take you to the reflexive polygons. So if omega is a lattice polygon, then you scale it by pair over vol, which is an integer. And so this is also a lattice polygon. And now, I have to, you get to use Pick's theorem, which makes me so happy. So you can use Pick's theorem on this scaling. Pick's theorem says that the area is equal to the number of interior lattice points plus 1/2 number of boundary lattice points minus 1. Area, remember, is, so vol was 2 times the area, or vol tilde, the vol of this guy. Number of boundary lattice points is exactly this notion of affine perimeter, And so you have one interior lattice point, which is these guys. And that's it. And then it's done. Of course, it doesn't tell us sort of geometrically what's going on, because these are like Fano toric varieties, but we didn't use that at all. We used Hicks theorem, which I'm always very well. Also, it's not a proof, right? It's just a conjecture. Okay, and then the thing that is missing is these do not have infinite staircase. We just check that they don't, and that's it. Okay, I'm done. Octal.
All right, thank you very much. So, of course, if there are any questions or comments, please go ahead. You can. I don't see any. Yes.
I have some undergrads working on symplectic embedding problems, and I told them that sometimes math is hard, and I told them about your foray into the online encyclopedia of integer sequences. Would you mind sharing that story with us?
Thank you, Joe. So, all right, let me zoom in on this part of the slide. Okay, so when, so let me say so what I've heard is that when Dusa and Felix were looking to understand their ellipsoid embedding function, they had these numbers, and it was in so the 1, 2, 5, 13, or rather maybe it was the ratios that they had. And you can correct me, both Felix and Dusa are here. And I heard that it was Dylan Thurston that said, oh, well, those seem to have to do with odd index Fibonacci numbers. So we had the same problem. We would get these heights of these staircases that we were encountering experimentally, and we would try to write them as ratios of two smallish integers and then see what sequence this was. So we would plug the sequence into the online encyclopedia of integer sequences to try to come up with what the next ones were going to be, and see if it had like a formula, like the Fibonacci numbers or the Pell numbers. And there was one time when the hit was this sequence. So it looks extremely like a recursive sequence: 2, 5, 8, 11, 13, 15. Of course, but this is the numbered stops on the Market Frankfurt Rapid Transit Railway line in Philadelphia. So this is so we have a way of predicting where the next stop is going to be if anyone is involved in public planning in Philadelphia. It has a symplectic. I'm sure we can work this into a grant. The other thing that is interesting is that Tara told this story to, who was it? I forget. To Tara can say. She told the story and they said, oh, that sequence, that is one of the sequences, let's see, where is it? That Sloan himself put in there when he was creating the online database, because he had to like put something in there, put some sequences in there. So this is like one of the original sequences from this database. All right, that's my story, Joe, thanks.
Okay, so there are some questions on the chat. So there's one from Egor. Go ahead, Egor.
Do the extra 4 polygons have rational A0? Yeah, so I see that Tara replied 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3. Okay, so this A0 is equal to 1, and this one A0 is a complex number. Or so I guess we wouldn't call it A0, because we said that A0 was a real solution. But
just a remark that's the 3, 1, 1, 1, 1, 1 case you were talking about in the beginning of the talk. Those.
Yeah, it was the 5. Yes, this is the one that has. This is one of the ones where A0 is a rational number. The other was this ellipsoid E34 that Dan is going to talk about in 4 hours, where A0 is equal to 3.
Thank you. Anna, when you modified So I'm mostly interested in staircases that touch the volume constraint. So you have 4. And now when you would like to prove the conjecture only there, is it then easier or not?
Oh, that's interesting. I don't know. I mean, this idea that this argument that I described does not use that. Does not use that fact at all. Because it only focuses on what happens at the accumulation point. But that's interesting. Maybe there's some other way that makes it easier. Also, Felix, by the way, I should thank you, because we couldn't thank you in the paper. But for this reason, let me explain. So when we were in this conference at in Stony Brook, at that stage, we had proved that there were infinite staircases, but we hadn't described the staircases fully. And you said, "You lazy pigs." And I have to say, for several months, it was like, well, now we have to do it, because if Felix then gets, like, when we send this paper to be refereed and Felix gets it, we're just gonna get a referee report that says lazy pigs, and he'll make us do the rest of the work. So thank you. We have a better result now because of you. But we couldn't write lazy pigs in the acknowledgements because.
No, I mean, Roger Gasal's idea is the key, right? Really.
Yeah, exactly. Yeah. Well, I think that. Dan, do you remember if the previous proof that we had did that?
Well, we had a existential proof. See, our original version, we just asserted the existence of infinite staircases, but we knew what they should be, but we didn't have a proof that they were, correct. And then Felix called us lazy pigs, and we felt bad. But I mean, in principle, we could have presumably done it without Casal's result, because, as Anna was saying, ECH capacities are sharp for this problem. So you could sort of play around with that, but it's not so easy to get the interior corners from that, because the ECH capacities are a supremum over an infinite set. So you need some kind of, the combinatorics can get substantial. And I think well, as Felix said, we were just, if you're a lazy pig, it's too substantial. So I don't know what would have happened without Casal's. I think it could have been done. Like, for sure, if someone had offered us, like $10 million, I think we could have done it. But with Casal's thing, it goes much more quickly. Yeah, for sure. I mean, one could also have done it somewhat like how you did it in your paper with Dusa, Felix, but then you have these like 12 different cases. I mean, maybe it's only 6, but again, we considered that, and it looked pretty tough. So certainly the Casal's thing simplified the situation a lot. I mean, one thing that's really nice with this ATF approach is you can just do it all in one fell swoop. So that's sort of my recollection.
Sorry, Anna?
Yeah.
So first, just mention Felix. So all these 12, they have full volume embeddings. I think Felix mentioned 4. I'm not sure if he misunderstood something. All the 12 that
No, they don't.
No,
They don't,
sorry.
Renato.
No,
Let me
you don't
just
touch,
show you.
only 4.
Let me go back to here. The ones that are in the big circle have full embeddings, and the ones that are in the smaller circle don't have full embeddings.
But they all have full embeddings at the accumulation point. It's just
Right.
in the corners.
Yes.
You're making the distinction in the corners.
Yes.
I made it on the whole stairs.
No, but that feels weird to me. That really feels weird to me. But we can discuss it later. I don't know. But because I think we did construct, we can construct full volume embeddings for all these 12.
I think that you have. I thought that I mean I looked at the paper, and I think that you have, let's see, it's 3-1 and 3-1-1. Yeah, so I
Oh
think you
yes,
have
9,
these.
9. No, sorry. Yes, right,
Yeah.
right. No, you're totally right. Sorry, not
Okay.
12. It's 9. It's
Okay.
9, but it's not 4. It's not 4. That's
No, sorry,
totally right.
it's
Yes.
4. It's 4 in the sense of 1,
Oh,
2,
the same vector. Yes. Oh, sorry.
3,
Yes. Sorry.
4. So there are 4
Yes.
different functions.
Okay,
So there are
sorry.
4 different graphs, I guess. 4 different
No, you're
staircases.
you're
But
totally
Oh,
4
right.
on there.
Graphs.
This not, yes, it's yeah. I forgot that these 3 were not. They didn't
Yeah.
touch. Sorry, it was my bad. But my actual question was not that. It was about like the Hilbert surface thing.
Mhm.
So, I mean, I would say that probably, I mean, this Hilbert surface, let's say, they are like the odd Hilbert surface, at least as you have drawn them for me, right? Which are the ones that are like blow-ups or ones of P2, right? And then you change the value of B, right?
Yeah.
And say in the limit B equals 0, this goes to CP2.
Yeah.
But the even Hilbert surface are the ones where the slope is the 1, 2, and the limit goes to the, if you want, the shape of the ellipsoid, the E12, which is equivalent to the polydisk, and so on.
Yeah.
I was just mentioned that probably the same techniques or the same ideas that you are using on this one should work on the
Well, I
other
think
one.
aren't those symplectomorphic to to these polydisks?
Yes.
So
yes.
that's more
Sure,
like
sure,
what
sure.
Mike Usher did.
Yes. Yes. Okay.
Yeah.
That's totally true. Yes.
But
Okay.
your methods with the almost toric embeddings would not apply when B is irrational, because you're in, or perhaps they.
It
perhaps
does.
they would.
It does.
Yeah, they would.
I'm not sure
I
why Roger once had this. Well, anyway, but it does. Whatever it is, we have never thought much about like looking into this, but it definitely.
Yeah, I think
I'm getting confused. The normals are rational, and therefore it does give you closed math. So you could apply.
Yeah. The thing that is confusing about ATFs, and well, the idea of like what would it do is the ones that are descending infinite staircases, because they're coming from the right. So you're starting with so you don't start with like your original shape. You'd have to start with like a very long and skinny ellipsoid, and then mutate it back to smaller.
Backwards,
or you start with 1 A0 and then you mutate it. But this is the limit, right? So I don't know. I'm really
no. Anyway, I mean,
maybe these don't have.
Was just a
maybe these don't
misperception.
have.
I missed that it was just equivalent to
Mm-hmm.
the polydisk that was already done by. Yeah. Okay. Sorry.
While we're on this slide, what is a blocked interval again? I sort of.
Oh, so it's B's. Oops. It's values of B's for which there is no infinite staircase.
And how do you, using our staircase theorem, I mean, how do you prove that there is no infinite staircase there, or is it just
each of those connected intervals? Each of those connected intervals is sort of blocked by a single perfect class. Like there's a single perfect class that forces the obstruction function to be above the volume at the accumulation point.
Yeah, at the A0 corresponding to that B.
I see.
Yeah, so you write A0 as a function of the parameter, and then you see certain classes are just going to obstruct a bunch of A0s.
I see. That's pretty cool. But so what happens between two blocked intervals? Is our staircase obstruction, I mean, so it you know, at A naught, if I'm between two of these blocked intervals, is it still usually the case that I'm above the volume curve? It's just there's not a clear exceptional, there's not a some kind of canonical exceptional class that's causing the obstruction.
I can tell you what happens then. We've suddenly found examples where there are blocked B intervals, and then at the end of the blocking, where it's not blocked anymore, we have a staircase, which will increase or decrease depending on how things work. And then it turns out that the classes in the staircase themselves are also blocking classes for different values of B. So it seems, you know, we have the set of blocked intervals seems to be it's possibly dense. It seems to be a union of open intervals. And our conjecture at the moment is, at least we haven't found a counterexample, is that at the ends of each of these intervals is a staircase. Now, Morgan is the one of our team who actually looks for staircases. So I very much hope she's going to investigate that. But, you know, everywhere we've looked, we've taken the most obvious blocking intervals, we've found staircases.
I see. But I think, so just to check to make sure I understood correctly, the blocked intervals that you put there are sort of just the ones you know about. Those are the odd, because
those are the ones we know about, yeah.
They could be dense in other, the blocked intervals.
We think it likely could be dense.
I see, okay.
Those are the ones we've proved, yeah.
Right, okay, that makes sense.
We think there are a lot more.
Cool, that's really cool. Thanks for explaining.
Yeah, but we're not using ATFs in what we do. We're using the same technique that Felix and I did with perfect, you know, exceptional classes, and sort of analyzing that, and also using ECH to help us with capacities.
And I guess one thing, sort of somehow you can also see the difference between the J equals 2 and the J equals 3 staircases, or sorry, the 2 periodic recursion and the 3 periodic. In the way these blocked intervals sort of vary as B gets close to 1/3. So that kind of explains the 2 periodic versus 3 periodic recursion.
Mm-hmm.
Or we hope it might.
Yeah, there are lots of very interesting questions that come up in this that you know, we're not there yet.
Well, there are 2 more hours of talks, so so one can expect progress. In any case, it was a great time to hear everyone talking about this. Maybe there are more questions. We have about 5 more minutes or comments. Well,
I have a lazy question. I could also look at the paper, but so when you're 2 periodic, then the mutation scheme is clear, right? You keep one angle, the good one, intact. And then you do left, right, left, right. So what is the scheme when you have 3 angles you want to mutate? Like ABC,
so let's see.
ABC,
so we
ABC,
need to put, yeah. So you have like this, right? And then let's see. So then when you mutate, so let me call this A, B, and C. So A moves on to here, right? And then B moves on to here, and then C is here. And so then you do B, and then B, that makes B move to here. And I don't even know where the thing is here. And then let's see, C moved here, and A is here, and so on.
Oh, you always treat the guy at the right down because
yeah.
Yeah. Thanks.
okay, so
Oh, sorry.
Sorry.
I think that picture really shows exactly why the J equals 3 comes up, because in the J equals 2, sort of a miracle happens and you're always just mutating a triangle so it stays a triangle and you're getting full embeddings. And the bottom line, where you have this 3-fold recursion, you always have a quadrilateral, and there's a tiny little sliver that you're missing, and that exactly encapsulates being above the volume curve at those points.
Right, right.
I think I'm going to put the first slide so that people know.
Oh yeah, right. And but by the way, in my talk, I'm going to say some more about how this staircase theorem is proved. So if you're
Oh yeah, I forgot to say that. Sorry.
oh no, that's okay.
For the proof, for heuristics and how this is related to the asymptotics of ECH capacity, go to this talk. For more about getting the full embeddings at the inner corners of infinite staircases, go to this.
And you
Para
actually
español,
left off,
oprima 3.
you left off your own name from the joint work. I mean, it's well, I guess, or maybe that's.
Oh, I see. No, I just copied.
Maybe I read it differently. Right. No, I see.
I just
I
copied
think I understand how you presented too, though. I mean, it's partially based on your joint work with us. Yeah.
Sorry. Yeah, that was I just copied the line above.
No, but I mean, yeah. But anyways.
This is very nice. I should also say, hi, Mark. I haven't seen you in so long. In case you're still listening.
All right. So let's thank Rita again. And thanks. So thanks.